And so to our lecture. So a former colleague of mine used to use the word jiffy to explain how quick he'd be back with an answer on something or how long it would take him to run an errand down the town. Based on this experience, I never really thought that a jiffy was any real measurement of time, and it certainly wasn't anything defined. But in the run up to this particular lecture, I was informed that a jiffy is indeed a defined unit of time. And for those of you who don't know, a jiffy is the amount of time light takes to travel basically the size of a nucleon, which in a vacuum, which is obviously a very short space of time. So it's not something my former colleague was ever aware of, and that's for sure. So this evening's talk will give us a unique insight into the history of time measurement from its earliest methods used by the Mesopotamians, to the Roman Empire, and to present day clocks. We will hear about sandglasses, waterclocks, sundial types, and the development of mechanical clocks and the marine chronometer. We'll also hear about the use of quartz crystal in time measurement and the invention of atomic and nuclear clocks. And we will delve into some examples of the critical use of time measurement in our everyday lives today, including GPS systems and mobile phones. And so to our speaker tonight, we're delighted to have Mr. Owen Duffy joining us. Owen qualified with a degree in agriculture back in 1968. He spent 30 years in advisory work in both Tipperary and Kildare before taking on the role of Agricultural Education Officer in the Sligo-Leitrim area with Teagasc. Owen always had an interest in things historical, antique furniture restoration, mechanics, genealogy, and very famously in 1990, Owen was invited to take part in the antique restoration section of the Late Late Show, you might remember, hosted by Gay Byrne. Owen restored a 1750 long case clock, and he actually won the competition on the night. This led to Owen developing an abiding interest in the whole aspect of clockmaking and clock restoration. While working in Kildare, Owen also got to know most of the main, I suppose, clockmakers in Dublin at the time, and he also joined the Antiquary and Horology Society. And through this society's lectures and demonstrations, I suppose it gave Owen an opportunity to build up a wealth of information and skills used in clock restoration. So I suppose Owen's the interest, I suppose, in clock restoration and time measurement has given an endless hours and days of enjoyment to Owen during his retirement over the last 10 years. And he may not have all the information and all the answers, who does, but he is an enthusiastic amateur horologist, and he's delighted to have the opportunity to share some of his knowledge on clock and timekeeping history with us here in Engineers Ireland. So he's kindly given up his time to prepare and deliver this talk tonight. We really appreciate you being here, Owen. And look at it, particularly given that we're presenting it over two different formats, both live on Zoom and here in person in the Sligo Park Hotel. So a bit of groundbreaking technology. So look at welcome one and all, and without further ado, I'd like to hand you over to our speaker, Mr. Owen Duffy.
Well, thank you very much, Ronan, for the kind introduction. And I suppose in terms of the jiffy, it's not too long ago that I was known as the late Owen Duffy. So first, before we go on to speak about timekeeping, I think it's important that we try to define time. It's important that we define time. Now, the scientists, philosophers, religious, the arts, they all came up with different definitions, but I think the physicist's definition of time is the progression of events from the past to the present and into the future. And the physicists consider it as the fourth dimension of reality, which is used to describe events in our three-dimensional space. Now, we can't touch it, we can't feel it, but the need and the desire to measure time has existed since the cradle of civilization. Before we look at the measurement of time, I think it's interesting to look at what alters time. First of all, we have the rotation of the Earth. We have the rotation of the Earth on its axis. And then in addition to that, we have the revolving of the Earth around the sun. So the Earth has two different types of motion. The revolution of the Earth around the sun takes 365 days and almost 6 hours. And of course, this is where our leap year comes from. In regard to the rotation of the Earth revolves on an imaginary axis that points towards the true north, as distinct from the magnetic north. And this particular line of rotation, it's at an angle of 66.5 degrees to the orbital plane of the Earth. That's the plane that the Earth revolves around the sun, and it holds that plane all the time. And just to give you an idea of the speed we're traveling at, even though we're sitting down here nice and comfortable, the Earth is rotating at the moment at the speed of 1,670 kilometers per hour. That's just the rotational speed. We'll talk about the revolving of the Earth later. It's another. Now, when we look at the revolution of the Earth around the sun, we see that it doesn't revolve in a circle, it revolves in an elliptical form. Sometimes it's closer to the sun, sometimes it's farthest away. On the 21st of December, the winter solstice, the Earth is closest to the sun. And when it is closest to the sun, it travels faster in its revolution around the sun. Then on the summer solstice, it's further from the sun. So it's traveling slower. And this has to do with the gravitational force of the sun on the Earth. The revolution of the Earth around the sun, it results in the change of the length of days and nights, and also in the seasons. And as I mentioned earlier, this has governed the way in which we live. The desire to divide the day into measurable portions, this desire has existed back as far as 4,000 years. And it led the Greeks and the Egyptians and later on the Romans to create several types of mechanisms to, or types of instruments to measure time. We had the waterclocks, sandglasses, timing candles, and later on sundials. Now, there's evidence that sundials existed in Mesopotamia and China in the 10th century BC. The water clock then, or the clepsydra as it's known, you have a container, or you had a container full of water, and the water dripped into a lower container, and as it dripped, it marked the passing of time. And of course, the time was announced then by the ringing of a bell. And importantly, no sun was needed to operate the water clock. The oldest known sundial then was made in Egypt in 1500 BC. The Greeks made several sundials in 560 BC, and the method that they had was derived from the Babylonians. And the Romans then adopted the Greek sundials. Now, Vitruvius Polio, he designed a sundial in 30 BC, and details of that are he was a Roman architect, and details of that are included in his manuscript. So really, the sundial is the oldest scientific instrument in existence. Vitruvius Polio also discovered that on a sundial, the shadow cast by a sloping object is far more accurate timekeeper than a shadow cast by a vertical object. He also discovered that if the shadow cast an object was parallel to the Earth's axis, The shadow at any given hour of the day would be constant, regardless of the season. Now, by the year 2000 AD, then, the Greeks who invented trigonometry into mathematics, they came up with the system of plotting the hour lines on sundials. And that continued to be used right up to the 20th century. So sundials were in general use up to the year 1700. And in fact, you had mechanical clocks invented at that stage, but the way they set the mechanical clocks was with reference to the sundial. The shadow cast by the central bar, that central bar was known as the gnome, and the pointer at the tip of the gnome, the style. Two types of sundials were made, the vertical sundial and the horizontal sundial that we're a lot more familiar with. The vertical sundial was designed for use high up on a south-facing wall, facing directly south. And the gnome then was pointing directly towards the true north. You can see it here. And when that was done, the shadow cast at 12 noon, or when the sun was highest in the sky, the shadow would be cast at 12 noon. Now, the reason these were erected high up on walls in cities and in monasteries was that a lot of people could read the sundial at the same time. This is a sample of a very early Christian monastic sundial. You can see the hole here for the, up at the top for the gnome, and the different prayer times marked on the sundial. That's in Kilmacedder down in Kerry. Then the horizontal sundial, every gentleman of means would want a sundial commissioned for his estate, and he'd get it made by an established instrument maker at the time. And of course, the sundial was needed so to determine the time that the household chores would be carried out. The sundial had the customary hour lines, and some were furnished with different tables, astronomical and calendrical tables. And we'll talk about the equation of time that was in sundials in a few seconds. They were always set on a graceful pedestal, usually in a rose garden, because that was the sunniest garden on the estate, and usually around 4.5 feet high, that they could be read with ease. This is a sample of a sundial made by a Sligo maker, Patrick O'Gara. Well made. He was a teacher, and teachers had a plentiful supply of slate, because the slate used in the last century and the previous century, the slate was used as a copybook. And also the school teachers had the mathematical instruments, and of course they had the expertise as well once they were interested. They made these sundials to teach children how to read the time. You can see the gnome here with OG written on it. This is on a different sundial, and I'd say it's strayed at some time from the original sundial. It was made in 1918. Now, on the sundial, as well as showing the time, on this particular one, you had another table. It was the equation of time. And when we look closer at the equation of time, we see that between the 15th of June and between the 15th of April and the 14th of June, we see down here clock slow. And then when we go on to later in June and July, we can see the clock is reading fast. So there's a difference between sundial time reading and clock time reading. The reason for this is, like we explained earlier, first of all, the plane of the equator is not the same as the orbital plane. We saw it was out by 23.5 degrees. And the other important fact is the rate that the sun's movement through the constellations changes over time. In other words, as the Earth is revolving around the sun, it travels, like we said earlier, the speed varies depending on the time of the year. The equation of time is to change the time on the sundial to match clock time. And here you can see the variation. It can be up to 15 or 16 minutes per day. However, we see that on the 15th of April, the 14th of June, the 2nd of September, and the 25th of December, sundial time is exactly the same as clock time. So this is basically an explanation of the equation of time that you get on sundials. So sundials are recording devices and they're embedded in nature. When we come to clocks, they're mechanical inventions. The hour now has replaced the day as the basic unit of time. So the problem with our latitude is that we have a lot of dull days. Sundials are non-functional on dull days. By the year 1300, artisans had set about building machines that would record time. These were usually in monasteries and connected with churches. And the reason being, say with the Catholic Church, they had 7 different prayer times in the monasteries during the day. They had matins, lauds, vespers, terce, sext, none, and compline over the 24 hours, different times to pray. And they were alerted by the ringing of bells. And of course, bells had been in use from the Bronze Age. So and of course, the bells denoted mainly church time in the 13th century. And the medieval belief was that time belonged to God. So as I said, the clock was primarily designed by the Catholic Church, the Cistercians, the Carthusians, the Dominicans, the Franciscans, and the Jesuit order. And of course, the Jesuit order eventually used clocks to encourage the royalty in China and Japan to convert over to Catholicism. It worked out for a while anyway. So the earliest clocks were of blacksmith quality. It was blacksmiths that were making the clocks. And the time was for monasteries. The clock time was for monasteries and the cities. Rural agriculture, the rural area went on sun time. The 24-hour concept then, that goes back to ancient Egypt. While the 60 divisions of time, that goes back to the Mesopotamians. And they favored whole numbers that could be divided evenly several ways. And as you can see, the 60 could be divided by 2, evenly by 2, 3, 4, 5, 6, 10, 12, 15, 20, and 30. Now, in the 11th century, the main power source was water. By the 12th century, windmills began to be in use with cranks, flywheels, and treadles. With the invention of the clock, a newer power source was being used, and that was gravity. So in designing a clock, there were 3 components necessary First of all, the power source, gravity, then a regulator that would regulate the power, and eventually a way to transfer that onto a clock dial or a face. Of course, the earliest clocks lacked a face. They didn't have a face. And like I said earlier, time was told by the sound of a bell. So that the name adopted for clocks, the name adopted for the new machine was clock. That's the Latin for bell, clocca, or also in Middle English, clock. That was in the 11th, 12th, 13th century. So as I say, the first clock being made, the power source was gravity. A clock weight, maybe a stone or a piece of cast iron, was hung from the mechanism or from the drive cogwheel. Then a form of regulator was called the escapement. That regulated the release of the power. And the escapement could be called the heart of the clock. And of course it was and is the escapement that causes the tick in a clock. The first escapement to be used in clocks was known as the Virgin Foliage. And by 1270, this type of clock had been invented. The power is transferred through maybe 3 cogwheels up to what's known as an escape wheel. And beside the escape wheel, you have a shaft that's called the verge. And onto which you have 2 pallets that causes the shaft with the power to oscillate. And on top of the verge, then you have what's known as the foliage. The foliage oscillates to and fro, and the speed that it oscillates at depends on how far out or how close the weights are to the verge. The closer the weights are, the faster the escapement works. This is just a sample of the weight, and here you have the escape wheel, the 2 pallets on the verge and the foliage on top. And this is a medieval clock, copy of it. And of course, the power source is a stone. There you can see the foliage oscillating, and it's been driven by the escape wheel. The weight is connected onto the drive wheel here. And a simple way, that's the cord that's connected to the weight. And onto the end of that, there's a pinion that engages with a pinwheel. That's actually the back of the dial. And when we look at the front of the dial, we see the dial is pivoting on a central shaft. And at the top, then, you have a pointer that marks the passing of time. Now, I let that cut in because for information on clockmaking through the ages, there's an invaluable source on YouTube. So that That particular slide is just taken from YouTube. It's a reproduction of a medieval clock, and it's in a museum in Copenhagen. I thought it was, you know, how simple the timekeeping mechanism is. Then in Salisbury Cathedral, you have the oldest mechanical clock in Salisbury Cathedral. Between 1300 and 1350, a lot of turret clocks were made. Some of the clocks were up to 2 ton in weight, bells up to 4 ton in weight. And at this stage, we had clockmakers. The first documentary evidence of a turret clock in Dublin was close to Christchurch Cathedral in the 15th century. By the late 17th century, the turret clock in the church tower in Blessington was made. And in Cork and St. Anne's Church, we had a clock that became known as the four-faced lyre. That was installed in 1847 during the famine. Maybe that's the reason. But the 4 dials of the clock never told the same time. By the 15th century, then, you had the development of the mainspring instead of gravity. And this was the start of the long road towards portability in clocks and watches. Now, the one thing about gravity, it was constant. With the mainspring, they weren't able to put the proper temper into the spring, with the result that the clock went fast when it was fully wound, and then it began to go slow as it unwound. Now, they came up in the 15th century with an ingenious invention. It was known as the fusee. And the fusee looked for all the world like a spinning top turned upside down. The fusee drove the mechanism. And the spring then was enclosed in a small bardle and was connected to the fusee by means of a cord or chain. When the clock was fully wound, the cord would be on the narrowest part of the fusee. And as the clock worked and the spring unwound, the pull on the mechanism would be on the widest part of the fusee. With the result, it was the start of improving the timekeeping using a mainspring. Then by 1583, the Italian physicist Galileo discovered the use of the pendulum and how it worked. He was in a church one day, the story goes, and he watched the altar light swinging and decided that it could be used in timekeeping. Now, he never created a clock, but by 1656, Christian Huguen completed the first pendulum clock. That was in The Hague, as I say, on Christmas Day, 1656, he completed the clock. Now, Huguen's clock still had what was known as the verge, but it didn't have the foliage that we talked about earlier. And this is just an example of the clock, the drive cogwheel, transferring the drive up to the escapement wheel, the escape wheel, the verge and the 2 pallets, but now it's controlled by a pendulum. And these clocks were designed to keep fairly accurate time, so that the day could be divided into 24 periods or hours. And the French system of dividing the day into two 12-hour periods was adopted, and the counting to start at midnight. In 1665, then, Fremantle produced a grandfather clock, one of the first grandfather clocks. And this grandfather clock, you can see the escape wheel here and the two pallets operated by the pendulum. And the reason grandfather clocks were invented so that the weights that was driving the grandfather clock had plenty fall. Here you can see the quality of the workmanship, handmade. And a very interesting point is that with the pillars of the clock that we see here, the earlier the clock was, the more ornamental the pillars were. So it was only after the development of the pendulum clock that the hour could be divided into 60 minutes, and the 60 minute or the minute divided into 60 seconds. So you're talking about 1656. By 1663, you had what was known as the anchor escapement developed. And this created a lot less friction. So it was a lot more accurate timekeeper. Here you can see the slight little bit of recoil, but William Clement in 1663 developed a clock that had this is thought to be the first clock with an anchor escapement. And the interesting thing about this clock, it was donated by David Bowles, a horologist in Dublin, to the Time Museum in Waterford that we'll talk about in a few minutes. So the escape wheel turns at a very constant rate. And in order to reduce, with the pendulum, in order to reduce air resistance, he designed it as a type of pickaxe style pendulum. As I say, to reduce. This is the internal part of the clock, again, all handmade. You can see that he introduced a mainspring and a fusee for improving the accuracy of the clock again. It's a gold-plated movement, and of course it has the silver chapter ring and the pickaxe-shaped pendulum. The other thing about this clock is that it only showed 30 seconds on the second dial. And like I mentioned earlier, this clock now had the anchor escapement. And as I said, this particular clock is in the Time Museum in Waterford. So long case clocks made their appearance around 1660, and this was to accommodate the fall of the weights. It was discovered as well in 1664 that a 39.1 inch long pendulum would complete a swing in exactly 1 second. And this became known as the Royal Pendulum. And of course, the long case clock could accommodate that pendulum as well. And with the development of these long case clocks, the time variation per day was less than 12 seconds. So now we were getting a new level of accuracy in clocks. So with the development of the pendulum clock and the anchor escapement, this destroyed the sundial's validity as the precise timekeeper. And of course, we had to have the equation of time on sundials then to match clock time. The earliest grandfather clocks were usually made in softwood and veneered with a high quality walnut veneer. Mahogany wasn't introduced or imported until the 18th century. And in Ireland, there was a ban on using oak because it was needed by the British Admiralty. So, as I say, mahogany didn't begin to be used until the 18th century. Here you can see a range of grandfather clocks in the Time Museum. The earlier clocks, like I say, were walnut, and you can see a lot of them had a little glass door, glass peephole in the long door, and that was just to see the pendulum bob. And as time went on, then mahogany came into fashion in around 1720, 1730, in the early 18th century. The slide was taken in the Clock Museum as well. The earlier long case clocks then, they had a very ornamental engraving on the back plate. And usually the chapter ring was silvered. And the way the chapter ring was produced, they etched the numerals on the chapter ring, and then they filled the numerals with engraver's wax. And after that, then they silvered the dial with a mixture of silver nitrate and cream of tartar. And there again, it's it's a fairly precise, it's a specialist job for doing it as well. But of course, the reason they silvered the chapter ring was so that the clock could be read later in the evening in poor light. Then by the year 1700, I'm sorry about this, by the year 1700, clocks only had made their way into the houses of the most affluent. Bankers, rich merchants, and estate owners. And most of our ancestors enjoyed a more leisurely approach to timekeeping. In 1670, Huguen, that developed the first pendulum clock, he also developed what was known, a new escapement, what was known as the balance wheel and hairspring. And this became eventually the mechanism that was used in pocket watches and our wristwatches. And here again, you can see the escape wheel. We can see the two pallets here onto the pallet fork, and that turned the balance wheel. And the hairspring then was to cause the oscillation. And as I say, this was invaluable in terms of the development later on of wristwatches or pocket watches and wristwatches. A big problem that they had then around 1700 was the whole aspect of measured longitude at sea. On the 22nd of October, 1707, 4 British naval vessels ran aground with the loss of 2,000 soldiers. So the British Parliament set the highest bounty ever in 1714 for a practical way of determining longitude at sea. And thus began the race and the row between the astronomers and the horologists. Both felt they could measure longitude at sea by their own specific, by astronomy or by clockmaking. With latitude, it was very easy to measure latitude using a sextant and measuring the angle created between the noonday sun and the visible horizon, and then using the National Almanac, a table that actually showed the latitude. So measuring latitude was quite easy. However, measuring longitude, it was discovered that there was a relationship between distance, degrees, and time. The equatorial circumference of the globe, 29,901 miles. It takes 360 degrees for the full revolution of the globe, and it does it in 24 hours. So working back down, we find that 1 degree or 4 minutes is equal to 69 miles. Or 1 minute of time difference equates to 17.25 miles. 1 minute of time difference equates to 17.25 miles. So if we know the longitude at the home port, say London, the standard meridian, and we know the time on board the ship, and we can compare the two, we know the time difference. So we know the number of miles east or west of the Greenwich. So basically the time difference converts into geographical separation or longitude. And a Yorkshire carpenter, John Harrison, designed the first marine chronometer in 1737 that could successfully measure longitude at sea. He perfected the chronometer in 1759. However, he wasn't awarded the bounty that was set by the Crown until 1779, when he was a very old man. In fact, his son was working with him at the time. And that was 20,000, which is the equivalent of 12 million in today's money. This is the fourth chronometer that he developed. And you can see the intricacy of the workmanship that he put into it. It was a height of 59 centimeters and a weight of 27 kgs. By 1759, he had designed his last chronometer. And this one was just 13 centimeters and 4 centimeters in depth. And as you can see here, John Harrison and Son, AD 1759. That chronometer is in the National Maritime Museum, and it's worth going to see it. It was an ingenious invention at the time. With long case clocks, like I say, from the 18th century on, mahogany began to be used. This is a clock that was made by a master clockmaker in Sligo, with the brass cherubs on the spandrels, and see the chapter ring. Originally, like I said, that would have been silvered, and it's 1750. And the clockmaker's name all was engraved on the chaptering, James Black. And as I say, he was 1750 in Sligo. Now, after 250 years, you can see the blackness of the works. And generally, before repairing a clock like that, you clean the works. And whatever bit of wear that's in the works before you clean it, when you clean it, you remove the oil that has caked on the pivot holes, so it becomes a lot worse than it actually was before you touched it. With the handmade clock as well, when you look at the plate of the works that's facing the back of the dial, you see, first of all, the hammer marks on the brass. Brass was hardened by hammering it. At this time, there were no presses. And also, you see the divider circles marking out the trains of the clock, the going train and the striking train. So it's a way of knowing that the works was handmade. The other thing we can see here, down at here, are punch marks, where somebody went restoring the clock by using punches to tighten the pivot holes again, which is sort of criminal. Now, when you go to clean the works, there's a mixture of ammonia, oleic acid, and distilled water used to clean the works. Here you can see the works of that clock cleaned. And that mix, it takes the dirt off the brass without etching the brass or affecting the brass in any way whatsoever. As I say, you can see the punch marks on some of the pivot holes. The proper way that these should be restored is by using a reamer with a set of reamers with a Morse taper, and centering the hole and reaming it out, and then inserting a clock bushing, inserting a clock bushing that it just grips the hole. And then it's hammered absolutely tight back into position. Now there's also wear on the pivots. So the pivots are cleaned and leveled, filed down, and then burnished, that they're absolutely smooth again. And once that's done, the hole in the bushing that's now flat on the plate can now be reamed out to suit the diameter of the new pivot. So by doing this, you're helping to make the clock close to being what it should be. On the later grandfather clocks then, when dials began to be mass produced, you had incorporated what was known as a false plate. You see the false plate here between the dial and the works. And that meant that the dial could be produced, and all that you were drilling to put the dial on was this false plate that was never seen. But it helps to date a clock, a long case clock as well. And this is typical of the Victorian type of clock that was made. There were a planar type of clock. This particular one was made by James Nelson, Sligo, and that was around 1850. So up to 1800, all the clocks were handmade. By 1800, two changes took place. First of all, the development of machinery in the States for mass producing parts. Mass fabrication of interchangeable parts. And the other thing that happened was the production of low-cost clocks in an area of Germany, in the Black Forest area. These are samples of some of the American clocks. The earlier ones was what was known as the OG clock, so-called on account of the mold, the OG mold at its front. These were weight driven with the weights on either side. And later then you had the American cottage clocks, 1860, 1870, and the steeple clock. And later still you had imported into Europe and Ireland what was known as the American drop dial clock. By 1900, a favorite wedding present was what was known as the American gingerbread clock, so called on account of the shape of the clock. It resembled the gingerbread man that they made gingerbread in the shape of a man in the States to encourage the kids to eat the bread. Also, you had the production of the American Waltham pocket watch in Waltham, Massachusetts. And these became very common in Ireland. A lot of them were sent home by immigrants. And as I say, by 1880, 1900, a favorite pastime was comparing what pocket watches to see whose clock was most accurate. In the Black Forest then, of course, they had a plentiful supply of timber, and they began making clocks that were mostly made out of timber. And the first clock that they began making in the 1800s was the same as the Virgin Foliage that we talked about. The German salesmen then, they traveled by the 1850s, they were making in excess of 500,000 clocks per year. And the clock salesmen, or as they were known as the clock peddlers, they walked the roads of Europe selling the clocks. Usually they had the clocks in what was known as the dragstool, which was for carrying the clocks, which were all flat pack. The only clock that was assembled was the one that was on the top. And they had that assembled that they could ring the bell as were passing by houses. They were dressed in their knee breeches, their white stockings, the silk waistcoat, the typical Black Forest costume is what they wore. And the clock that was sold mostly in Ireland was what was known as the wag on the wall. It cost around a guinea in 1880. And people paid for these clocks. It was the first form of hire purchase. They'd pay ½ crown every quarter for their clock. And of course, a lot of the clocks were never fully paid for. A lot of the clock peddlers disappeared as well. And when the clock peddler was asked where he was from, he'd respond that he was Dutch. So of course, in Ireland, these clocks became known as Dutch clocks. And of course, later on, then the Germans continued on making novelty clocks, Black Forest clocks, and singing bird clocks and such. So as I said, the wag of the wall was the first clock that was found in farmhouses and cottages and in the town dwellers as well. And we have to remember that around 1900, there was no phone, there was no radio. So people still depended on church time, or maybe the sound of the passing train from the 1860s. This particular clock then, a very well made clock for checking people in and out of work. It was the mechanism and the mechanism for stamping the card that were made out of what was called tool steel. Very high quality steel. By World War I, pocket watches had been reduced so much in size that they could be worn on the wrist. And this improved timekeeping of the timing of operations during World War I. Self-winding watches made their appearance in the 1920s. And radio broadcasting technology was soon to revolutionize timekeeping. Now, we were talking about very accurate clocks, only losing 12 seconds per week. Now we're going into a different realm of accuracy. In 1880, the properties of quartz or silicon dioxide was discovered as early as 1880. And of course, it was used in radio technology. Quartz is what's known as a piezoelectric material. In other words, if you have a piece of quartz and you hit it a rap, it creates an electronic impulse. And the opposite is true. It was discovered that the quartz vibrates at a very regular rate when you pass an electric current through it. It oscillates at a frequency of 32,768 times per second. Now, if you have that number 15 times, you finish up with 1 or 1 hertz, 1 beat. And the electronics of the watch does that job. So you have 1 vibration per second, with the result that when you look at a quartz watch, oftentimes you see the second hand and it jumps from minute to minute, whereas on most of the mechanical watches, it travels at an even speed. So in 1928 was the first time that the quartz was discovered for timekeeping at Bell Laboratories in New York. And it was as revolutionary as the pendulum. Quartz now is used in all our clocks, in our watches, in our mobile phones, in our computers, and even in our pacemakers. The first quartz clock was installed in the Royal Observatory in 1939, and it only varied by 0.002 of a second per day. By the 1950s, the accuracy had increased to 1 second in 30 years. And we might think this is very accurate, but there's more to come. It was only in the 1960s, I think 1969, that this technology made its way into the wristwatch. In 1948, then, the first atomic clock was developed in Washington. And it was a more precise and more stable timekeeping source. And it worked on the atom's resonant frequency. In other words, oscillating between 2 energy states. The cesium-133 atom was developed in the 1950s, and that has the accuracy of 1 billionth part of a second per day. So that since 1967, the new definition of the second is based on the frequency of the cesium-133 atom. The atomic clock based on ytterbium takes trillions of times a second and is highly stable. And this particular clock is accurate to the femtosecond. Now we're talking about 1 millionth of 1 billion part of a second, or 1 quadrillion part of a second per day. And This sort of timekeeping is very important when we come to measuring outer space or in GPS. Lilestein, writing recently in Popular Mechanics, wrote that the latest atomic clock based on entangled atoms is so accurate that its timing over the entire age of the universe would be less than 10 milliseconds off. In regard to GPS then, the GPS that we use is the United States system. And they have 31 medium orbit satellites revolving around the Earth. And each of these has an atomic clock. And with my GPS or my mobile phone, the satellite can beam down on my mobile phone, take the time that I received the beam and the time that the signal was sent, and subtract one from the other and multiply it by the speed of light. And that gives the distance in an arc of a circle. So in order to establish the exact position, you need three satellites to beam. And of course, the speed of light is just someplace less than 300,000 kilometers per second. Now, the big problem then with GPS is the atomic clocks are accurate, but my receiver is not as accurate with the quartz technology as the atomic clock. So you have what's known as the time offset. So what's needed is a fourth satellite to solve the offset problem. So when we connect our GPS, there are actually 4 of the satellites in medium orbit that are beaming down to give the exact location. Another problem is the whole Einstein's theory of relativity. Atomic clocks are traveling at the speed of 14,000 kilometers per hour. A clock that's traveling fast slows down. That's the reality. Time isn't absolute. So the time on the clock slows down by 7 microseconds per day. The other thing that happens is that these satellites at an altitude of 20,000 kilometers above the Earth, the satellites experience only quarter the Earth's gravity. With the result, this has the effect of speeding up the clocks. So the clocks speed up by 35 seconds. So net, there's a speeding up of the atomic clocks on account of the theory of relativity by 28 seconds. So there's a theory of relativity equation incorporated into the computer chips in the atomic clocks to take care of this. Without this, the GPS would produce an error of 10 kilometers. And basic GPS is accurate down to a few meters, down to 6 or 7 meters. Or an error of 1 microsecond will produce an error of 300 meters on the ground. So our system was developed by the United States Department of Defense, and it's absolutely free. The Russians have a different system, the Chinese have a system, and Europe is developing a system as well. What they're developing at the moment is the deep space atomic clock. And this is based on a mercury ion. and it's built by NASA's Jet Propulsion Lab. And it's 50 times more accurate than the standard atomic clock that we use in our GPS. It's designed for space navigation into the future, and it's completely stable. The DSAC-2, which is being developed at the moment, will be used in NASA's Veritas mission to Venus in 2028. And they're using all the data that they discovered from DSAC-1. Finally, they're working as well on a nuclear clock using the isotope thorium-229. And I suppose much like Harrison's marine chronometer of 250 years ago, the nuclear clock and the updated atomic clock will be vital for exploring outer space. The fact that you're dealing with such distance. Now, I think I've overshot the runway, but I should mention before I finish that a place that's well worth a visit is the Museum of Time in Waterford. And two amateur horologists, David Bowles and Coleman Curtin, they donated their complete collections of clocks to the museum. And it's unbelievable the way the history of time is dealt with in the clocks that are on display in the sundials. And I think that Eamon McEnany, Rosemary Ryan, Clean Purcell has joined our Zoom webinar tonight, and they're very welcome to join it. They're doing a fantastic job. And it's in Greyfriars Street, which is in the Viking Triangle in Waterford, just beside very inexpensive car parking. So it's well worth a visit. And that more or less concludes my few words. I've run a few minutes over. I'm sorry about that, but I'd like to thank Ronan and the committee for inviting me here tonight. And if there's any questions, I'd be delighted to take them. I mightn't answer them, but we'll have a shot anyway. So thanks very much.
Owen, thank you very much for that. An absolutely fascinating presentation. They say every day is a school day, and I think we all learned a lot there this evening. So what a tour of the history of time measurement, from 2-ton clocks to deep space atomic clocks. When you started talking that we were traveling at 1,670 kilometers an hour just sitting here, I started holding on to the chair, but very, very interesting talk. So look, we might open it up then to some questions. A reminder for those of you online to type your questions into the Q&A section. Not the chat box. And then for those of you here at the venue, the mic is open here through Francis. That's Maureen's, yeah. So just one comment here initially, Owen, from John Mead. He was saying the Irish for both bell and clock is the word clug. And this makes sense from the Latin origin of the name as you described. And he's often wondered this, and he says, thank you very much for explaining the origins of the name. So well done.
Thank you, Ron.
Thanks, John, for your question. Just a couple of quick questions just to spring to mind. You didn't mention Big Ben there at any stage in London. How does that date in terms of age, or where does it fall into the greater scheme of things?
Yeah, yes, well, Big Ben, the funny thing about Big Ben, it was developed, the tower was built, and the clock constructed during the Great Irish Famine. They began building the spire or the turret in Westminster in in 1842. They completed the tower in 1859, and Denison constructed, he developed the clock, the clock that's known as Big Ben. In fact, Big Ben is actually the bell. In 1859, a bell was made for the tower, and they had it in the palace yard at Westminster, and they were trying out how it would sound. And the bell was struck 2 or 3 times, and the next thing the bell cracked. So the next bell was made in Whitechapel Bell Foundry. It's down beside the Bermondsey, or beside the Tower of London. And this bell was brought as 13.7 ton in weight. And it was pulled down from Bermondsey by 16 dray horses on a dray. And it was hoisted up to 200 yards up the side of the tower. Who was involved in the arranging of the bell was Benjamin Hall. And he was involved in the construction and also the construction of the clock. And he was 6'4" in height. So somebody mentioned at one of the meetings in Westminster that about Big Ben. And this is where the name came from. The Big Ben is the name of the bell. But of course, it is a very famous bell and a very famous clock. Now, shortly after Big Ben was installed, it cracked as well. And what they did was they cut out the area that had cracked in the bell, so that with the Westminster chime, there's a very sonorous sound from the bells. But when Big Ben strikes, you know, the dull sound that you have from the bell. The reason for that is on account of the damage to the clock in 1860 when it was installed. So it is, of course, it's world famous on account of the sound of that bell. But, and of course, they're working on the restoration of the bell at the present time. One of the companies that maintained Big Ben for over half a century was a company named Twayton Reed in Clerkenwell in London. Now, the one thing about Twayton Reed, there's a turret clock locally that was installed in 1820 in Collooney, in St. Paul's Church in Collooney. That was made by Twayton Reed as well. So we have a little bit of history in Sligo that's associated with Big Ben, or the company that maintained the clock.
Very good, Owen. It's very interesting. One other quick question for you. You mentioned earlier on that when the clocks appeared in the 1600s, that they appeared in the houses of the most wealthy in society, bankers and merchants. I noticed you didn't say engineers there for some reason, but
or agriculturalists.
Yeah, but I'm just wondering, like, how do people train to become horologists? Like, I mean, it's obviously a craft that's handed down to generations, is it?
It's well, usually it'd be the son of a clockmaker that would go into clockmaking. Now, back in the 18th century, clockmakers, there was an apprenticeship in clockmaking, and it ran for maybe 4, 5, or even 6 years. And once a person had successfully completed the apprenticeship, they were then known as a journeyman. They were approved for their apprenticeship. Clockmakers were under the guise, they were under the direction of the goldsmiths company. And this is one of the reasons why most clockmakers, you see, in earlier years, they were working with very valuable gold, silver, platinum, and Henry VIII, for example, in around 1540, he presented a gold watch to, I think it was his fifth wife, Catherine Howard, in 1540. And in 1542, he beheaded her. But that'll tell you, you know, he presented her, and that's on record with a gold timepiece. So, as I say, clockmakers were under the goldsmith company's umbrella. Once they trained as a journeyman, they spent 3 years, which were known as the journeyman years. And they traveled around to different master clockmakers, doing work. Eventually, what they do was to produce one masterpiece themselves. And that would be submitted for assessment. And once that was sufficiently good, they became a master clockmaker. So it was a long period. As I say, journeymen had to complete 3 years working with clockmakers. They couldn't work on their own. And of course, all clockmakers then, masters, had to make subventions to the goldsmiths company every quarter. So it was a long period of training, but it was usually clockmakers' sons or daughters that would follow the profession. Now, what happened in 1968, when the mechanical watch was coming under threat with Quartz, the Swiss set up a Swiss School of Horology in Blanchardstown in Dublin. And this was to train clockmakers in the art of mechanical clockmaking. And it was a fantastic college, but of course, the mechanical clock didn't win out. Quartz won out. And I think it was around 1990, the college closed down. That was the Swiss School of Horology. A lot of clockmakers, present clockmakers, were trained in the Swiss School of Horology.
Very good, Owen. Just a quick message here online as well. Highly interesting talk. Thanks for sharing and allowing everyone to attend. Really enjoyed when tuned in from Cork. That's from Tim Cronin. I think we might have another message from, or another question from the.
No, it was just a question from myself. Well, it was a bit drastic what Henry VIII had to do to get his gold watch back from his wife. But in the equality of the sexes, I was wondering, you know, if the long case clocks, there were no grandmother clocks, were there, or why grandfather? Or can you shed us a bit of light on that?
Well, I suppose, you know, the proper name for the grandfather clock is the long case clock. Henry Clay wrote a poem in the States, I forget what year it was, about the grandfather clock stopping working when the grandfather died, and it stopped short, never to go again, when the old man died. So as I say, after that, it became sort of known as the grandfather clock. Now, there were grandmother clocks and granddaughter clocks. They were all slightly smaller than the grandfather clock. So I'm sorry to being sexist in my talk tonight.
Owen, thanks for that. A question here from Barnes Murphy. He says, hi Owen, that was a fantastic presentation, very interesting and informative. Can you explain why the weights on a typical grandfather clock are different? I understand one weight is for time and the other the bell, and why the difference in weight?
Well, the weight of a grandfather clock weight, they average around 12 pounds. The going train works on that weight of 12 pounds. Sometimes you have a weight of 13 pounds on the striking train. Depending on the mechanism, it takes the extra piece of weight. And of course, if the weight happens to be too heavy, then the clock will strike too fast. The fly won't be able to counteract the weight. So it can be 13 pounds. And the other thing about the striking of the clock, say sometimes if the bell on the clock is too loud, what some people might do is put a piece of elastoplast where the hammer strikes the bell, and that can soften the tone of the bell. A lot of the younger generation don't want the sharp strike of the bell, so it's an easy way of softening the tone down to whatever level or pitch that you want the bell to strike at.
Very good, Owen. Another couple of comments online here. Not a question. This one is from Rosemary Ryan. Not a question. Just wanted to thank you. Absolutely wonderful talk, Owen. Thank you very much. And the organisers, fascinating. Delighted I was able to attend. David Bowles and Coleman Kern have been great teachers, and has been great to be able to learn and deepen my knowledge through the actual timepieces. Learned a lot tonight. So much useful stuff to share with our visitors at the Irish Museum of Time, which I think you mentioned earlier on in Waterford. A question from Rosemary as well, just going back to the battle of the sexes here. How many female clock or watchmakers do we know of in Ireland, especially around the 1700s, or maybe any in the 1600s, or would you be aware of any?
No, not really. A good reference, Geraldine Fennell drew up a list of clockmakers in Ireland in 1926. In the 1990s then, in the 1990s, William Stewart, I showed the vertical sundial that was erected in 2001 in memory of William Gallen Stewart. That was erected at his house in Selbridge. Now, William drew up a book before his death, and it was edited and finally produced by his wife, June, and David Bowles. And that has over 2,500 clockmakers that were in Ireland listed. So I'm not sure of the exact number of male versus female, but I know that the number was very small.
Okay.
Now, maybe it was on account of the long, arduous craft, the apprenticeship and the journeyman years afterwards. So it's the thing I must look up in the, as I said, Geraldine Fennell produced for the National Museum a fine record. That was the first record of clockmakers in Ireland.
Pretty good.
I think by 1901, there were up on 900 clockmakers in Ireland by the 1901 census.
Very good one. Okay, we won't hold too much longer. There's a few nice messages coming in just from Kieran Horgan. Fascinating, wonderful presentation. We could listen to Owen all night. I think we'd all agree with that. Thank you very much, Owen, for the most informative and fascinating talk. Are most watches now digital or analog, would you say?
Most watches are digital at the present time. Now, for a number of clock companies, both in France and in Switzerland, they are making very expensive mechanical watches. And by expensive, I mean you could pay up anything up to maybe 50,000 for them. They're collector's items, so that they're you know, and there are newer types of escapements introduced into them that I didn't talk about tonight. But it's mainly the digital quartz watch that we're accustomed to today.
Sorry, Brian.
Thank Owen for the most informative lecture. I knew Owen when he was doing turnips in Sweden, so it shows that he has studied so widely of this area. And I'm just looking back at almanacs.
Brian, sorry, could I interrupt there? Just would you mind speaking into that mic there, just for the benefit of the people online, if that's all right? Sorry, now.
And just to thank Owen for a fabulous lecture. And I've known Owen over the years, and having studied horticulture, he knows more about turnips and Swedes. So also such a fabulous lecture. Just one, looking back on almanacs and that of Sligo. Have Sligo many, I know you mentioned 2 or 3, had Sligo many more clockmakers and watchmakers in Sligo?
Yes, Sligo had upon 20 clockmakers, genuine clockmakers. The earliest that I came across, they would be German origin. There were Whirlies. Of course, they go back to the 1870s. You had James Black, you had John Irwin. There's a clock of John Irwin's made in Sligo. It's in Castletown House in Selbridge. You had Molyneux's, you had Roy's, you had Little. There was upon 20 clockmakers, and in fact I have wrote an article this year on the clockmakers of County Sligo, which will be in the Ballymote Heritage magazine, the Carden Herald, and it describes all of the clockmakers that were listed in Sligo up to the present. But there was upon 20 clockmakers in Sligo. The reason why Sligo had so many clockmakers was because, say, especially in the 1820s, 30s, they had a very active port. And of course, a lot of clockmakers came in through Sligo port. And the fact that you had a fairly active port, you had a lot of merchants. And of course, you had very big timber imports into Sligo, so you had raw material as well, you know, and back even during the time of the famine. So Sligo did have a lot of clockmakers because they had a lot of rich merchants in Sligo, and you can know that by the type of houses that were built back in Georgian into early Victorian times.
Okay, Owen, thank you very much. Some very complimentary comments coming in here online. One from Frank Leach there, Rosemary as well, and Eamon McWeeny there in Waterford, commending you on your talk, and looking forward to welcoming many of our listeners to Waterford, to the museum. Maybe the last question I might ask you, Owen, is maybe two parts. One, how did you get into this whole business originally? And second of all, what kind of a watch do you wear yourself?
Well, I got into it by default. I was, somebody put my name for, I was into furniture restoration, mainly furniture for her own house and pieces that I liked myself. And from that, I often heard, I remember Brian Coyle from Adams, he was a valuer in Adams. Brian used to always say, well, if you could make a hood for a grandfather clock, you could make a grandfather clock. And I never saw very much difficulty into doing that. I thought that should be a simple job. So eventually then when my name was put forward for the Late Late Show, I happened to restore a Georgian clock. And of course, that whetted the appetite for the whole aspect of restoration and the unbelievable mechanical genius that was put in at a time when they were handmade. So from that, the love of restoration developed with me, clock restoration. And of course, then I began going to clock fairs in Brunel University and Middlesex. And I mentioned Bermondsey Street. There was a market down at Bermondsey Street where they dealt mainly in very good clocks and watches. And I attended that on several occasions. So one thing led to another, and it has given many, many hours, days, and weeks of enjoyable sort of hobby. And exactly the same as this talk tonight, the research of it has given me a new sort of lease of enjoyment, and it helps to keep the mind active as well.
Very good. And what kind of a clock do you wear yourself?
I wear, it's Geneve. Now, it's a digital clock that I bought in Cyprus about 20 years ago. And it's the case, and the strap is white gold and ordinary gold. And I only wear it on very special occasions. I have a turn-up that I wear when I'm in the workshop or normally. But
so look, we're privileged that you brought out the good watch for us tonight. So Brian, Owen. So look, I think there's plenty of other comments there, but I just conscious of time. So I suppose, look, we might just we finish there if that's okay. Look, on behalf of the Northwest region, Owen, I'd like to say a very big well done and thank you for once again for all your time measured in jiffies. The effort you put in to tonight's talk, we can really see your enthusiasm and your depth of knowledge really comes through. The quality of your slides, you put a huge amount of work into it. Really mesmerizing stuff, and we hugely appreciate you giving up your time to prepare and deliver tonight's presentation and for sharing your knowledge of all things timekeeping. So as a token of our appreciation, we'll have a small hamper winging its way to you in the next couple of days. So we might show our appreciation for Owen in the usual way. Finally, I might just say a quick word of thanks to my own committee here for their assistance in organising this talk, in particular to John O'Gorman for all his help in delivering and organising this event, and to Francis here as well for helping us deliver it blended online and in person. Thanks to the Sligo Park Hotel for helping on the technology front. Great to be back here in person. Thanks to Maureen in Engineers Ireland, who's behind the Zoom webinar here, for all her help. She's so generous with her time and for managing the Zoom platform for us. Thanks to everybody who attended, particularly those of you who came out to the Sligo Park Hotel tonight, and those of you at home on Zoom for participating. And we had over 70 people attended the talk, Owen, which is a fantastic turnout any night of the week. So again, thank you very much to everybody. And now, look, we just go and ask you maybe to just check all the clocks and watches in your house, make sure they're all in time. So thank you very much again,
Thanks
Owen.
very much,
okay.
Ronan. Thank you.
Yeah, cheers. Thank you.